In the previous video, we're talking about external quantum efficiency and saying it's less than the internal quantum efficiency because something can happen to the photons that are produced before they make it out of the LED so that you can see them or so that they can be detected. One of them is that the photons could be reabsorbed by the semiconductor. Another option that's shown in this figure is that, if you're emitting photons, so here's an emitted photon that would make it out of the LED structure. Here's a photon that is emitted, but it's emitted in the wrong direction, so it's traveling for a significant amount of time through the semiconductor, and eventually it just gets reabsorbed. Another example is this photon being emitted in this direction. If you put a reflective coating at the back of the LED, this photon will still have a chance to make it out of the LED. It hits this reflective coating and it's going back out, but only if its lifetime is long enough to allow for this travel time, or so that the travel time from going here, hitting the reflective coating, and then getting out of the semiconductor, if that travel time is less than the lifetime. Otherwise, it's going to get reabsorbed. So all of these factors make the external quantum efficiency less than the internal quantum efficiency. This figure shows some examples. External quantum efficiency is a measured quantity. So external quantum efficiency in this graph is on the y-axis. On the x-axis is the acceptor or doping concentration. So you can see how the external quantum efficiency depends on doping concentration. On the bottom graph, this is fixing the doping concentration, but the external quantum efficiency is varying as a function of junction depth. So junction depth means, this junction between the p and n-type materials, how deep is that from the surface.